I'm Yavor Nenov, and I'm the CSO of Oxford Semantic Technologies. What Oxford Semantic Technologies is a spin-out of University of Oxford. You will recognize some of the academic founders, Ian Horrocks, Bernardo Cuenca-Grau, and Boris Motik. They're all very well known in the community. What do we build? We built RDFox, which is a high-performance knowledge graph management system and a reasoning engine. Quick overview of what RDFox looks like. It takes as an input some data, which typically is presented in RDF. It also takes as an input a knowledge base, which could be your OWL ontology, bunch of swerve rules, or rules, RDFox rules, which I'm going to talk about later in more detail. So RDFox takes the knowledge base, the data, materializes all the consequences, and the system is ready to be queried with Sparkle queries. So the materialization with zero reasoning overhead during query answering. Another critical feature of RDFox is incremental updates. RDFox can handle updates of data and knowledge base incrementally. We have developed very efficient algorithms to handle such kind of updates. And we have other features such as persistence for fault tolerance, constraint validation, access control. These are like features that are not very interesting from DL perspective, but are very critical for our customers. We also have access to external sources such as databases, file systems, and full text. This is the overview of the system. In terms of reasoning language, RDFox's reasoning language is based on Datalog. It is an extension of Datalog. So you have all the restrictions that come from DL on conjunctions in rule bodies and tonality, and row chain inclusions are no longer necessary. In the case of Arity, we're still primarily working with RDF data, so our internal data is represented as unary and binary relations still, but algorithms don't really require that. We also have negation as failure and aggregation as part of the rule language, and also manipulation over your data, like arithmetic, string manipulation, and so on. In addition, we have scoring functions, which are useful for many things, for representing, for example, n-ary relations, and but can also be used for example, combined approach to query answering in EL and other fragments. What about existentials and disjunctions? We know that they're useful for schema reasoning, taxonomical reasoning, schema definition. So it's a very useful feature. You can use your ontological reasoner to complete your taxonomy, bring that to RDFox. RDFox will consume that and perform the relevant reasoning with your data. When data is concerned, however, we've noticed that typically axioms that mention disjunctions and existentials, these are usually intended as data constraints. And these are very simple kind of data constraints which are easily expressible in the RDFox rule language, particularly due to negation as failure. So a little bit about the implementation. RDFox is main memory and materialization based system. Main memory, why? Because it's much more efficient and we have plenty of it these days. And materialization allows us to be able to answer queries with zero reasoning overhead. You have the query, that's what you answer. Over your materialization, no reasoning overhead during query answering. And rewriting approaches don't really apply for these more expressive rule languages, such as RDFox's one. So how do we implement it? Well, we rely on these highly memory efficient data structures, and also which also allow for lock-free updates. And these are critical for our reasoning algorithms that we've developed at the University of Oxford. because they're parallel, scalable parallel materialization and incremental reasoning algorithms that require such kind of data structures, details in the publications that you see below. So just in terms, a few numbers to see that plausibility of the whole approach. You can load 2 billion triples in a particular use case. We've tested 2 billion triples in 5 minutes. More than 500,000 triples materialized in around 2.5 minutes. Simple queries take a couple of seconds, and intensive updates take in the order of 25 milliseconds. So again, this is incremental reasoning. Note on the right-hand side has nothing to do in terms of time, which when you compare to initial materialization. So these are the incremental reasoning algorithms that take place there. So how do we build semantic solutions using RDFox? Other speakers already have alluded to the fact that there are two types of users. Some users that care about, know about description logics, know about ontologies and want to use them, and other which are less interested in those. But our experience is that typically larger corporations, they are aware of the technology and they do care about ontologies. So the way RDFox is typically used in these kind of scenarios is you have your schema definition defined in Protege, class hierarchy, role hierarchies with different properties like transitivity, symmetry, and so on. You can define your swirl rules as well. And you can also define an extended knowledge base, which uses the full power of RDFox, graph analytics, data analytics, local, simple constraints, and also global constraints, and combination of the above. So in the, as an example, we have a configuration management use case where you have a company that wants to sell assemblies of components. You have multiple large number of components that have to be assembled in a particular way to get you a large component that then you can buy. So you have to be able to answer questions like find all rotating solutions, assemblies that can spin at 2000 RPM and provide a certain amount of torque. So the data is the description of your basic components with their properties, and then the ontology defines these components in terms of what kind of features they have, and the rules and more complex rules. You can define which components are compatible depending on their properties, and also to define your assembly templates, so that the ones that you want to build from components. So these are all defined in the rules, and negation as failures was particularly important in that particular use case. Another example is the design safety use case. The task is to ensure engineering designs are safe, they meet requirements and comply with constraints. The input data is your model, your design description, which comes from your CAD system or whatever it might be, annotated with appropriately so we can actually reason with it. And the ontology describes the different components, types of components, how they relate to each other. And again, the rules encode the requirements and the constraints that need to be met. And then incremental reasoning is again critical in this particular use case, where as soon as an error comes in, and the engineer can change it and immediately see the effect of that change, whether it has been what they have hoped for. So hopefully this gives you a little bit of indication how we use RDFox in practice. Open to questions later on.